One of the most difficult aspects of programming. Understand the problem. What does that mean? You actually have to define your problem before you can solve it. And some problems are extraordinarily complex just because there are a large number of factors involved. Like if you're writing a large video game with multiplayers, lots of things to keep track of. Well, that's a you know a difficult problem to solve. It's a whole bunch of problems that you're going to have to define very carefully. But anyways, any program you write for somebody, including yourself, you're going to have a roadmap in your mind in order to figure out what you're going to do. You're going to have to understand exactly what you want it to do, because the computer will do exactly what you tell it to do. And if you didn't tell it to do the right things, it's not going to work. So you need to consider the users, or the people for whom the program is written for, and the documentation, which is supporting paperwork for a program. Now, if you work in a large organization, there may be teams of people who write documentation for your programs. Nowadays, it seems like you get a game and there is no documentation, right? Because you don't buy games, on DVDs with little booklets and stuff like that. But anyways, it's likely that if you work in an organization where you are providing programs for somebody, there's also going to be documentation coming along as well that the end user needs. There will be a trail of paperwork going from the initial requests to the specifications and requirements, and then the manuals for using the software, right? And that can get all, as much or as little as is necessary, but you can just assume that some documentation is going to be required, even if it's just a rewrite of the specifications, right, to tell the user how to use it. And inside your program, in the comments, you will also be documenting your code. You'll put an explanation of what this file does and some explanation of the logic. You'll be doing those with the comments. So, planning the steps of the program and what they include. The algorithm is a sequence of steps that you use to follow or solve a problem. You have different planning tools. There's something called pseudocode, which is just kind of loosey-goosey English. It's not a programming language. And then there's flowcharts. And desk checking is when you walk through a program's logic on paper to make sure, before you actually write the program. Pardon me?
It's like a rough draft.
Yeah, a pseudocode is a rough draft, right? It's not written in a computer language. It's written in English, but it shows the logic. Yeah. So coding the program. There are hundreds of programming languages available. And broadly speaking, they're similar in their basic capabilities. The vast majority of programming languages are what are known as procedural programming languages or object-oriented programming languages. There's one more kind called functional programming, which is a strange beast. But in general, you always have loops. You always have the ability to store data in variables. You always have, the ability to write decisions with if statements, and you always have the ability to declare functions and modules that you can then invoke in the program. So they all have similar basic capabilities. Supposedly, the coding is actually easier than the planning step. And when you're writing your programs, you're going to say, no way, but that's probably because the planning wasn't careful enough. And honestly, it's really, really tempting just to start programming without the planning, right? You sit down, you go, okay, I'm going to need this, and I'm going to need that. And you're going to see me do that up here because the problems that we solve in here are things that I've already written, 100 times, and so I don't have to think much about, the 101st time I've thought about it. So I'm not going to be writing a pseudocode or a flowchart for every program I solve. And I'm not going to make you do that either, but there will be times. So experienced programmers can successfully combine logic planning and program coding in one step. That's just what I mentioned. When you have a program, you have to compile it, or it has to be run through a compiler or an interpreter. Now that happens automatically. You don't have to think to yourself, well, I'm going to choose a compiler or an interpreter. If you have idle, if you have Python been running, and then you have a program, open one of last week's programs. All right, there's a little program. This is not machine language. It's not zeros and ones. So, did I do the chip in a box drawing up there? Did I get up and draw pictures? Okay, I'll do that. Y'all may find it amusing, you may not. Anyways, this has to be turned into the commands that a computer can understand. The computer has no idea what this means, and so that step is known as compiling. And so I am going to veer off, and we're going to do our How a Computer Works lecture. And this is slightly silly. It's a very, very simplified explanation, but I'm going to go for it anyways. What do we have? We have a guy here. He's stuck in a box. His name is Chip. That's real funny. Everybody can laugh. This is the central processing unit of your computer. He's got some scrolling paper. It's infinitely long. Well, maybe not infinitely. Your computer doesn't have infinite memory, but right, you might buy a 4 GB computer or something with 8 GB of RAM. So it's got 8 billion different lines. 8 billion different places to write on. You've got a pencil, right? He can read and he can write to his scroll of paper. That's address 0, that's address 1, that's line 2, that's line 3, that's line 4, that's line 5, and so on. So that's his memory. To help him keep track of things, he's got a couple of other things he can write on that are inside the chip. These are technically known as registers. They're just places where he can write some numbers, so while he's doing math or whatever, he doesn't have to do it in his head. So we're going to say that he's got 3 registers, R1, R2, and R3. But Chip doesn't understand English. He only understands some kind of machine language. We're going to make up his machine language. We're going to say that if he sees a 1, he's going to read from his paper. And if he sees a 2, he's going to write to the paper. And if he sees a 3, he's going to do an add. Might be enough. These are known as operational codes or opcodes. The people who designed the chip, Intel or the ARM Corporation or whatever, create the opcodes. And of course, modern chips with their billions of transistors or whatever have extraordinarily long operating codes, in order to do all sorts of things to operate very quickly. But a very limited subset of operating codes would be enough to prove the point. Like back in the in the early 70s or whatever, integrated circuits were first invented. They didn't have to have millions of opcodes in order to write something that would control a pocket calculator or your Apple II or whatever. So we're going to give him a program. You're going, what in the heck? It'll get there. It'll get back. And we need a 4th command, a jump command, which jumps back to an earlier line number. Okay, so we just have all these numbers. What in the world? What in the world? Well, we're going to replace this row, this column, with their English commands, just for our head, just for our sake, right? So that we understand. Chip doesn't want them translated in English, but we do. Otherwise, this isn't going to make any sense at all. So command 1, read. That's a read. I should not have erased them all because I'm having trouble. That was an add. That was a 3. That was a write. That was a 2. So it's a write. And this is a jump. All right. Don't get too bored yet, guys. Okay, so these are Chip's instructions. Read, read, add, write, and jump. Now, what are these numbers? We're going to say that this is the memory address and that this is the register. So he's going to read from address 0 to register 1. He's going to read from address 1 to register 2. And now he's going to add register 1, register 2, and store the results in register 3. Then he's going to write the results of register 3 back out to memory address 0. And then he's going to jump back to the first instruction. And we always start counting at 0 with computers. We'll see that over and over and over. Zero-based indexing. So jump 0 is going to go back to the top of the instructions. All right. So get to work, Jim. We don't have any data stored in here. So everything's got a 0. Memory address 0, 1, 2, and 3, all the way down to the end of the line are all zeros. Okay, so read from address 0, write it in address 1. So he's got a big 0 there. Read from address 1, stored in address 2. Now for this to work, we're going to actually need some non-zero data in here. So I'm going to fake it and say that something has come along already and put a 2 into that address. Something needed to have changed it. I didn't write a longer program to stick that in there, so just let me fake it. So read from address 1, stored in register 2, right? And that's what it's in address 1. What's the next command? Add. Add address 1 and address 2 and store in 3. Okay, what's 0 plus 2? It's a 2. The next command, write from register 3 out to address 0. Okay, what's register 3? It's a 2. There, that's our new memory. That's what we've got. And then go back to the top. Okay, we're going to clean out these registers. What's the result of the first command? Read from address 0 and store in register 1. Well, what's at address 0 now? 2, right? Next command, read from address 1 and store into 2. What's at address 1? Right. And then 3, add register 1, add register 2, and store in register 3. 2 plus 2 is 4. Write from register 3 back out to 0. We would write the 4 out to there. And then jump back to the top of the program. It's going to keep adding 2 to it over and over and over. Right. Now there should be some kind of decision making. Right, so like if, it hits 10 or something, it jumps to the end of the program and stops. Otherwise, it's just an infinite loop. It keeps repeating forever. But fundamentally, that's what's going on. It's just following a set of instructions. You saw how at one point, it was just all numbers. Even underneath that, it's not just all numbers. It's all zeros and ones that get translated into numbers according to some scheme that, the people who develop the hardware and the software agree upon. And that's called binaries, when it's all zeros and one. These numbers here were called the machine language. The machine language uses the opcodes, and they're fed to the chip to make them do things. That looks a lot different than what our code did when we were writing Python. We would not want to have to write like that. We definitely would not want to have to write like that. That's old style programming before the invention of programming languages in the 50s. Yeah, there were computers before the 50s. They were strange looking things. That's not even the one I'm thinking of. That's not even the one I'm thinking of. Dadgummit. There we go. That's more. The ENIAC. Yeah, there we go.
Wasn't that where the term bugs got from?
Mm-hmm. You've heard that story. You stole my story. No, I'm kidding. So, if you look at this, what's going on here? The programs were actually written by wiring the hardware units together with patch cables, like, you know, old-time telephone. You know, place a call to room 3, you know, and put the cable from there to there. Or if you're a synthesizer user, you use the idea of patching your modules together, whatever. So, typically, the newspaper articles of the day would show a bunch of important-looking men standing in front of the computer, and then they might show, you know, some women back there doing things with it. The way the educational system was set up then is that invariably the hardware engineers were males. The women enrolled in the war effort were like, you know, MIT math professors or whatever, because that was the educational path that was available to women. And then they were, you know, trained, they were given the hardware specifications, and they pretty much were on their own to figure out how to actually make the computer do things. So it's fair to say, for this and for another reason, that the first programmers were women. It's just kind of interesting that over time, up to about 80s, the 70s or the 80s, if you took computer programming courses, it was like a 50-50%. You know, division, and then past a certain point, not because the work got any harder or something, it was just kind of a cultural shift, right? The programmer, the hardware guy, I mean the software guy, right? You know, anyways, it's kind of interesting that you see these people, and now books have been written about them, and everybody knows all their names, and people know the names of the people who wrote the first programming language named COBOL. One of them was Grace Hopper. So she invented just about the first programming languages in the 1950s. Why would you want a programming language? Because you wouldn't want to have to sit there and write those numbers, right? And to punch those in manually into the computer. You'd rather be able to write something that looks like English and have the computer turn it, you know, teach itself that those English words means all the zeros and the ones and whatever. And so she was the one who, the first computer bug. It's taped in her journals, right? First actual case of bug. Well, why is that a big deal? Well, back then, computers were made out of vacuum tubes, which is just a fancy kind of light bulb, you know, and if the bulb is dim, it's a 0, and then if it's got a charge, it's a non-zero value, and mechanical relays, right? Things that closed in order to send current and opened in order to stop the current. If you get one of those guys, you know, in your mechanical relay, it can't close to send the current along. So you see the term actual case of bug. That means that the term bug was a previously used term, not really in programming. Programming was a new discipline at the time, but, you know, I've got to work the bugs out of the system. You know, electrical engineering, who knows, Thomas Edison may have said it or something like that. It's kind of interesting that the first computer bug is forever enshrined under a piece of tape, you know, some Smithsonian book or something like that. So it's what we're trying to do, is to write stuff, English-like commands, that get changed in all those zeros and ones. So when we press the run button, what happens is the program gets written out to disk, right? Then the compiler runs through it, changes all of these words, you know, to the zeros and ones and the opcodes that they need to be, and runs it. And if that does not work, if it does not work because of a syntax error, then it can't run. Either that, or it may run up to that point and then crash, but you saw that it just flat out could not run. It could not create a series of opcodes. It could not create the binary necessary to actually start running because it didn't know what we meant. It did not follow the syntax correctly. So syntax error, you make a mistake in the grammar rules. You correct all the syntax errors. You might need to recompile the code several times. Often in some programming environments, like if you're using the C++ compiler, you try to compile it and it lists like 200 errors, and you panic. I wrote code that's that bad? No, you fix one error and then 150 of the errors go away. And you fix the other error and then the rest of them go away. Right. It's just that once it hits a mistake, things go off the rail. Right. Once you you drove off the side of the highway, all sorts of bad things are going to happen. Right. You can hit trees and houses and stuff. So it's just one error at the top, and then another, and then another, and then the vast majority. Idle isn't like that. It just tells you the location of the first one. It doesn't list them all the way C++ does, because that's kind of misleading. But if there's a mistake in the program, not in the syntax, but in the program itself, let me write something that I know is going to crash. Dividing by 0. I know, as a matter of fact, that that's going to crash. Division by 0. It tells me where the problem is. It tells me the purpose of the problem. It might tell me what the code looks like, but very, very, very important, it tells me where. Now, it would be really nice if when we were looking at the source code, it had line numbers on it. 1, 2, 3, 4, 5, 6, 7, 8, and so on. It doesn't. However, if we look down here, there's a little line number counter, and if you move your cursor around, you can see the line number change. So when it says that there's an error in line number 64, you just have to keep moving your cursor up and down with the cursor keys of the mouse until you find yourself positioned on line 64. We're going to get real used to debugging, because I don't write perfect code. Y'all aren't going to write perfect code. So we're going to spend some time looking for syntax errors. I almost never do it deliberately up here just to show it to y'all. But invariably, I'm going to make mistakes. And then if y'all are following along with me, then y'all are going to make the same mistakes. So you're going to make up your own mistakes. And we'll have to find them in order to get our programs to run. Pardon me? So testing the program, you can have logical errors. Here's about time for me to start taking notes. So I'm going to make a new file. I'm going to do a save as. I believe this is our third lecture, so I'm going to call it lecture C. I'm going to put a comment block up at the top like I want y'all to always do. Don't put my name, right? That's enough, right? We don't have an explanation of the program itself because we don't know what program we're writing. So I'm just going to put chapter 1 notes as my explanation of what we're doing here. All right, but now I'm going to open a multi-line comment so that I don't have to just keep putting in, hashes in front of everything I type. So, broadly speaking, 2 kinds of errors. 1, syntax errors. 2, logic errors. Syntax errors are when the program can't figure out what to do. It hits a point that it just can't be turned into machine language, right? It's like I give you a recipe, but I use a word that you have no idea what it means. Maybe I meant it to be the word sugar, but I typed it in as, D-I-H, RT, because my fingers were off by 1. You would not know that that was supposed to mean sugar, so that's a syntax error, right? Did not follow the correct grammar. Mistake in grammar or typos. And then logic errors. You get the syntax perfectly right, but it does the wrong thing. The sensor picks up that you're following too close to the other car in front of you, and so it applies the accelerator. That's a logic error, right? Does the wrong thing is kind of vague, but right, anything a program can do incorrectly, right? It can calculate and display the wrong answer. It can draw the wrong thing on the screen. It can quit when it wasn't supposed to quit. It cannot detect that Pac-Man has hit the ghost, and so Pac-Man sails to the ghost, which is fun for you, but you know, it doesn't make for following the game rules. Or Pac-Man just sits there and immediately dies. I'm going to show you all an example of a logic error. I really hope when I say Pac-Man, you all know what I mean. Screen 255 Pac-Man. Or 256 is what I should have said. Well, this didn't show reaching it, but there we go. That's a logic error. What has happened is the player has played through 255 levels of Pac-Man. In other words, they're insane. So, they played 255 levels of Pac-Man, and then Pac-Man tried to draw the 256th screen. Now, the data to hold that number 255 was actually just 1 byte. Memory was really expensive back then. 1 byte can hold the values 0 through 255. A byte is 8 bits, right? 8 zeros and ones. The guy who programmed Pac-Man never imagined that somebody could last through 255 levels of the game. And even if they did, then, you know, big deal, they played long enough, right? You know, they played their hour and a half or however long they got there. You know, it'd be okay if the game ended at that point. But he just had no comprehension that anybody would do that. So he never handled the case that once they hit level 255 and you add 1 to level 256, there is no level 256 because that's too big to store in a byte. And so it got changed back to a 0. It's trying to draw level 0. There is no level 0. Right? There's a level 1, and then it goes on from there. And so when that happened, it drew garbage on the screen. So that's, you know, early video games, a lot of them had flaws like that, where you could play them up to a point and no further. Like in Donkey Kong, there's a kill screen where the character just dies as soon as he takes 1 step. You know, you've played for 2 or 3 hours, and it finally gets to a point where he just dies as soon as he takes a step. And a lot of y'all probably have played with video game emulators where you download something to your computer so that you can play old stock games or Nintendo games or PlayStation 1 games or whatever. Some people figure out these mistakes and they correct them so that you could play Pac-Man forever if you were absolutely insane, or, you know, the kill screen on Donkey Kong wasn't there or whatever. So that's an example of a logic error. Then there's a third kind of error that I do not believe that the chapter mentions, but I'm going to mention it, which is a runtime error. A runtime error is when the program hits a state from which it cannot recover. Now, what does that mean? You try to save a file, but the disk is full. You try to access the internet, but the internet is down. You try to divide by 0. Well, leading up to the division by 0 might be a logic error, but it's a runtime error because the hardware does not know what to do when you divide by 0. That's just there's all sorts of jokes and memes and stuff like that about dividing by 0, right? If you Google divide by 0, you'll see, yeah. Okay, sorry for the bad language. For the last time, stop dividing by 0. Divide by 0. Congratulations, your math just destroyed a city. Okay, you know, silly things like that. You just can't divide by 0 because in terms of math, you can't divide something by nothing. Now, some people say that if you divide by 0, the answer is infinity, but whatever. So the computer is going to crash. It's going to encounter a runtime error when we try to divide by 0. And the reason I keep talking about divide by 0 is not because it's the world's most common programming error, but it's because the easiest to demonstrate, right? I can just do it in 1 line of code. Right. So a runtime error is program reaches an invalid state. Disk is full, bad file name, hardware failure. You tried to write past the end of memory, you have 8 gigabytes of RAM, and you tried to write to gigabyte number 9, giga meaning billion more or less, right? Things like that. Now that doesn't have to crash your program. Programs can handle errors, And so a runtime error and the failure to handle a runtime error could be considered a logic error. But conceptually speaking, they're two different things, right? A logic error would be to turn, the wrong way on the way to Walmart. The runtime error is running out of gas. And yeah, it was a logic error to not get some gas on the way to Walmart. That's fresh in my brain, right? Running out of gas thing. So, I guess I could give those as silly examples. Logic error, turn right when you wanted to turn left. And runtime error, car runs out of gas. Car gets a flat tire. Now you probably have used computers long enough to have seen the error message. Windows has encountered an error and program will terminate. Something like that. So you lose your term paper because you were writing it in Word and it says Windows has encountered an error. Yeah. Programs are not supposed to do that. They're not supposed to bail out like that. They're not supposed to let the operating system kill them. Instead, they're supposed to accommodate errors. But programs are also exceptionally large and complex things, and they're working with large and complex operating systems, and so you do have programs that just flat out crash. But the goal is to write programs that handle the mistakes we can predict. We are aware that users are stupid and might type in words rather than numbers. So our programs can take that into account. Otherwise, you could get a runtime error when you try to convert those words into a number to do some addition. Now, let's give an example of that. We're going to write a program that asks for some input so that it can add, so it can double a number, right? If you type in 3, it's supposed to print 6. So I close my multi-line comment with 3 quotes. Print, parentheses, quote, please enter a number. Number, end quote, in parentheses. Now we have to get that input. We have to let the user type something in, which is done with the input command. And we need to store the results in a variable so that we can print it out or double it or whatever we want. So x equals input, parentheses, in parentheses. And then how about x equals x times 2? We're going to double the number. Now, I've forgotten an important step, but I'm going to leave it in for now. It's a programming error, but it's going to be a runtime error as well. And then we're going to print the result. So it's a logic error that leads up to a runtime error. The result is, so print, parentheses, quote, the result is, end quote, comma, x, in parentheses. That's a little program. Roughly speaking, the pseudocode for this would be input x, multiply x by 2, output x. That would be our pseudocode for it. I'm going to run it. Please enter a number. Now, I can't really see where I'm supposed to be typing. I don't like that, so I'm going to make the program a little bit better so that we can see where we're supposed to be typing. Inside the parentheses of the input statement, we can put something, and if we put something there, it gets displayed on screen. So I'm going to put quote greater than end quote to let the user know where they're supposed to type. They're going to see that greater than sign and hopefully know that that's where they're supposed to type. There. I like that better. And I'm going to type in 10. 10's a number. The result is 1010. All right, now honestly I was expecting it to crash, but that's still not our intended result, right? We wanted it to say 20. If I change the math here to like divide by 2 instead of times 2, we would see our syntax error. So I'm going to change that to a /2 just to get, not the syntax error, runtime error, just to see it cough up an error. And there we go. We got a runtime error and it crashed. And it looks like gobbledygook. It looks like, speaking in, in Greek. Unsupported operand type for the division sign, string, and I. Alrighty, that's a lot of information. A lot of almost incomprehensible. At least it tells us the line number, and it tells us the line of code in which it accompanies. Now the problem is that we typed in something. It was just a series of typewritten characters. Could have been anything. We typed in a number, but we could have typed in the word hello, right? Or we could have typed in, grabbed a Korean keyboard and typed in a whole bunch of symbols there. The computer doesn't know what to do with that. It's not a number. It hasn't been converted into a number yet. And so the input we get from the keyboard is not something ready to do math with. Just like if you get sugar to add to your cake, you better unwrap the sugar first. You better open the bag, right? If you just throw the bag of sugar in the bowl, you're not going to get a good cake. So we need to convert this input into a number so we can use it. Now, there's basically, broadly speaking, two kinds of numbers. There are ints, integers, and there are floats, floating point. Integers are whole numbers only. I'm going to make it a float so that if the user wanted to see what 3.3 divided by 2 was, they could type in that 0.3, which would not work for an int. So, before that division line, I'm going to add x equals float parentheses x. Please enter a number, 67. The result is 33.5. Now, it'd be nice if we gave them a little bit more information, like dividing by 2, and the result is 33.5. Maybe we'll put that in there as a print statement, right? So above this one, above that print statement, I'm going to add one more. Print dividing by 2, ... end quote, in parentheses, or maybe I don't have to, however I wanted to word it. Now it's a little bit better of a program. It explained what it did. Please enter a number, 90. Dividing by 2, the result is 45. So we have a working program. We could still crash it if we thought we needed to type in a number, because it told me to. Could not convert string to float. That's because this is not a valid number, and when the program tried to turn it into a number, it can't, right? Because that's meaningless. It's not a number. Or if it was asking for a price, enter the price that you wish to bid, and you typed in a $sign and it wasn't expecting a $sign. Well, it would fail. Now we could make it handle the $sign, but we didn't, so it crashed. We got some bad input, and so it crashed. Now your programs can take that into account and try to handle things like that so it doesn't crash if the user types in something unexpected. And we could make it handle a $sign, but we didn't. Okay, so if we had written the algorithm for this, the pseudocode for it, it would have looked something like this. This is what's known as pseudocode. It's going to have the word start, just kind of like if you go into a mall and it says you are here. You need to know where to start. And so we're going to do we're going to do the simplest one. Input x, set x equal to x divided by 2, output x. That's our algorithm. Now, obviously, there's a lot of details we left out. Even this looks like a programming language because I kind of made it look, very specific. But I could have said divide x by 2, storing the results in x, right? Or even just divide x by 2. Something like that. Or, I could have said x equals x divided by 2 and left off the word set. The book wants us to use the word set. I don't care. I'm going to go ahead and put it there. All right, so that is pseudocode. It's simplified. It doesn't show every step. It's not written in any specific programming language. And if you give pseudocode to a programmer who understands Java, they will write a Java program that implements this. And if you give it to another programmer who speaks C#, then they would write a C# version of it. It's language agnostic, right? It doesn't specify the language. It doesn't specify any specific syntax. The way you implement this syntax in C++ is completely different than the way we do it in Python. There are some commonalities. I could write it in C++ and show it to you. It looks something like this. I don't necessarily want y'all to write it down, so I'm not going to even put it in our notes. But it would look something like this. C++, every line ends in a semicolon. All right, significantly different. And this would have to be enclosed in what's known as a main function. But even leaving out the fact that we have to have a main function, that's what the C++ code looks like. It's different, right? But it's the same kind of stuff. We just had to declare our variable before we could use it, unlike Python, which will declare it when it needs it. Whoopsie. This is an output statement. Instead of print, it uses a cout thing, and it uses these weird little symbols. This is an input statement. Doesn't use the word input. Instead, it uses that word and those two symbols. And here's some math. This means divide equal to. In other words, take x divided by 2 and then store the result back in x. And here's another print statement and another print statement. Similar syntax, or I mean similar ideas, completely different syntax. And the programmer who knows that language would turn our pseudocode into that instead of this. Pseudocode can get more sophisticated than this. We could have printed the messages, right? I left off the fact of telling the user what to type in because I just did. But I could have put an output statement here telling the user what to do, right? Output, enter a number, right? I could have done that. And then this one right here, this dividing by 2, I could put that there as well. But I'm just going to delete that for now to show you that the pseudocode could be the simplest possible thing for it. That make sense, guys? Anybody got syntax errors and your code is not running at this point? I'd like to fix it so that as we keep typing, it's good. Nope. All right. So testing it is when you run the program with sample data to see whether the results are logically correct. Well, we've kind of done that. The act of testing the program. I run the program. I type in something. And boom, I've got a mistake. I've got a syntax error. The mistake is that I opened a multi-line comment and forgot to close it. Meaning that I have a triple quotes, but then I forgot to put my closing triple quotes. So way down here at the bottom, I'm going to need some triple quotes at the end of my comments to get convince my program that it works. All right. There, I have now tested my program. Is my testing done? No, you don't just test with one piece of data. You test with several pieces of data. You try to spot some errors. Right? So, okay, 0 is a common failure point, right? 0 divided by 0. Okay, whew, that worked. Then run it again. Right. Okay, now people often think that they ought to be able to do this. Well, I tested it with 90. Now I'm going to test it with 0. Well, the program's not working anymore. It's not, because we have to run it each time. Now we can make the program loop so that it jumps back to the first instruction, but right now it's not looping. So it runs once, and then it stops. And if we want to run it again and find out that 200 divided by 2 is equal to something, we actually have to run it again. Can't just type in 200 here and have it do the math. I guarantee that while we're testing this stuff, somebody's going to be showing me the program. They're going to run it, and then I'm going to tell them to try it again with a different number, and they're going to just type that number. Not because you're dumb. It's just because that's the way you expect it to work, right? That's the way all of our programs work. You don't just launch, you know, your MP3 player, pick one song, and it quits, right? It keeps going. Well, these programs don't keep going until we tell them to, until we add a loop in order to get that to work. Now, debugging is a process of finding and correcting program errors. You type in some data, and it doesn't do what it is supposed to do. Example, what if I had done this? My code said divide, or my pseudocode said divide x by 2. All right, I've divided x by 2. Right? So I run it. I type in 100. Dividing by 2. The result is 100. No, it did not divide. It did divide by 2, but it did not keep the results. Right? It's like writing a note to yourself and then throwing it away. Right? It did the division, but it did not store the results. That's why we had to have that line. But it can be, there's a term I'm looking for, and it's not seductive. Subtle, that's the word, right? Please enter a number, 0. Dividing by 2, the result is 0. Whoa, I got my program working, right? I tested it. Well, you didn't test it adequately because any non-zero data would have shown the error. If I run it and I type in 50, and it says 50 divided by 2 is 50, now I know that there's an error. So what programmers do is they test their program to see if it runs. That's just how we are. We've written a program, we want to see it run. So we run it, it runs, we feel a sense of triumph. But if it's professional software, you also need to test it to see if you can make it fail. And quite often you have different people doing the testing for you. You've got to test it yourself, but there may be an entire testing department. You can be sure that a big company like Electronic Arts probably has hundreds of people devoted to testing their various pieces of programs, right? Because it's really important that that stuff works. And so you have a testing department, you have a programming department. Well, we are our own testing departments, except I'm also the testing department, right? I find errors as well. I need to fix that. So if you made that change, make sure you undo it. Get back to saying x equals x plus divided by 2. So the programs should be tested with many sets of data. Now I had a test question once, or a quiz question that said, how do you test a program? 1, you run it once. 2, you test it with all possible data. 3, something else. And they argued vehemently that yes, you should test it with all possible data. You want to make sure it works in all circumstances. It's impossible to test with all sets of data, right? I'm not going to test it 1, 2, 3, 4, 5, going out to infinity, right? I don't have that much time. I don't have an infinity number of days in order to test it. So instead, you test it with particular numbers, particular values. You're smart about it. You pick a good representative subset, and you pick things that you suspect might cause errors, right? So you pick careful values, but you can't test it for every possible value. Whoever's writing the video game cannot predict every single series of joystick presses because there's an infinite series of joystick presses you could do, right? Even if they don't seem right. You know, you get Pac-Man up against the wall, you can start waggling your, your controller left and right and left and right and up and down, and he never moves, but, he got some input, and, but we can't test all possible input, but we can test with many sets of data. Now, these simple programs, we only have to, test with a couple pieces of data to prove that it worked, right? I ask you to convert Fahrenheit to Celsius. I happen to know the boiling points and the freezing points of water for both Fahrenheit and Celsius. And so if I test it at those 2 points and I recognize the numbers, I'm pretty sure it works. And if I didn't tell you to make it error-proof, it'd be okay to not handle the user typing in garbage, right? Garbage in, garbage out. If they type in letters, it's not going to be able to turn it into a temperature. When I give you an assignment, I could give you numbers that I want you to test it with and expected results. I might not, but for the temperature program, maybe I know that 0 degrees Celsius is equal to 32 degrees F, which it is, and I could tell you that. I could say, write a program that converts, this to that, type in 0, make sure you get 32. Type in 100 and make sure you get 212, that kind of thing. Putting the program into production. If it's a complex program, if you're writing something for the government and they have to install it statewide or nationwide, it can be a big, big thing. Or, to get it published on Steam for other people to download, it's a whole series of steps. Anyways, putting the program into production. Putting it into production means making it available to the users. Conversion. The entire set of actions an organization must take to switch over to using a new program. We've upgraded the system. We stopped writing it in COBOL. It's now written in C++. It's now a web app. We've got to convert it. We've got to get all of our users up and running on the new system. Maintaining the program. That's making changes after the program is put into production. I've uploaded the program to Steam. There are players using it now, and they're all running into the problem where, they go to level 3 and then the king disappears, and so they can't finish the game. Well, you got to have somebody there in order to fix it, or else the game, people are going to get frustrated. You never publish an update, they'll never be able to finish the game. Or, video drivers are infamous for needing to be updated. They have teams of people working at, NVIDIA in order to handle the errors so that they can publish a new set of drivers so that, games don't crash or display incorrectly or whatever. So maintenance programming is a common first programming job where you didn't write the program to begin with, but you're fixing it, right? Oh, what do you know? It says that right there. I'm not so smart. It was on the PowerPoint. But I was going to say it anyways. Maintaining previously written programs, and then later on maybe you get to write your programs yourself. And I'm talking like if you're working, professionally. If you get hired by a company in order to work, that may be your first programming job. So pseudocode is the English-like representation. I gave you an example of it. Input X, divide X by 2, output X. That's pseudocode. And a flowchart is pictures, a pictorial representation. Oh, well, what do you know? Their problem looks almost exactly like mine, except I put a divide there, right? Pseudocode representation of a number doubling program. Start, input my number, set my answer equal to my number divided by 2, output my answer. They use 2 different variables there. I just used the same one all the way through. My logic was as good as theirs. Theirs is perhaps slightly better in as much as if they later needed to use this original data again, it's still hanging out, right? If now we were going to divide it by 2 or add 2 to it, well, when I did it my way, when I said x is equal to x divided by 2, that erased the prior value of x, right? No longer did I have the number 50 hanging around anymore. I had 25 because I reused the same variable name. Yeah, but that will certainly make a lot more sense as we go on. So pseudocode standards. Programs begin with the word start. They end with the word stop. And these words are always aligned. And then you start tabbing over. Now that's different from our coding language where we didn't use any tabs, right? We had all this code here. We had, that was Monday's program, or last Wednesday's program. We had this code here. It did not have the word start, and it didn't have any tabs. That's because that's pseudocode. Every language looks different. Remember when I was writing at C++, if I was going to finish the example, it would need something that looked like this. Do I want you to learn C++ while I'm doing this? No, but I'm giving you examples of different syntax. There, right? Again, that's the code for this, pretty much. Unfortunately, there's even 2 more lines of code we'd have to add. You can see why we're not learning C++ as our first language, because I was able to do in just a couple of lines of code, which is taking a lot more, There. Now that is a complete C++ program. That's a lot more than we had to do in order to get this to happen, right? A lot of this you have to do for every single program you write. You have to have some of these statements up here at the top. You have to have that stuff. You have to have this stuff. It's kind of called boilerplate, right? Fortunately, we don't have to include all that boilerplate. We can just sit down and write some code. If I wanted to just do, you know, x is equal to 1 divided by 2, or if I just wanted to print hello world, you know, print hello world, like that. By the way, that \n means new line, means go to the next line. It's like hitting the enter or the return key. Okay, there's my hello world application. I could have written this in one line in Python because I don't need all this boilerplate. But this looks different than the pseudocode, right? Doesn't have the word start. Does have some tabs. Pseudocode always begins with the word start. It does not follow the specific syntax of the language, and everything inside it is tabbed. And then sometimes you have some stuff that's tabbed over 2 times or 3 times. We will see examples of that. And every statement performs one action. Some input, some processing, or output. So the programs are indented more than the start. Each program statement appears on a single line if possible. If not possible, continuation lines are indented. What does that mean? Well, if I was writing some pseudocode, I'm going to undo this, so don't write this. But what if the equation was more complex than just divide by 2? What if it was a complex mathematical formula that went off the end of the, end of the screen? I'm not going to give you, Okay, I'm just going to do some copying and pasting, right, so that I can pretend it's going off the screen. Okay, now that's valid pseudocode, but it's kind of dumb. It's going off the edge of the page. So instead, I might want to do this, right? These tabs just mean that they're a continuation of the last line of code. Now, can we do that in Python? Yeah, sort of. We use a backslash at the end of each line. If you use a backslash in Python, oh, I actually added that into Python rather than the pseudocode. But you can use a backslash to indicate that you wanted it to go to the next line. Like x divided by 2 plus backslash 10 times 20 plus another backslash 30. Right? That's valid code, and the way you read it is as though those backslashes weren't there and those new lines weren't there. New lines meaning where I hit the return key, going to the next line. I'm not going to do that very often. I'm not going to go to the next line very often. Only if I go off the end of the page will I do that. That will happen to me more often than you, right? Because your font is itty-bitty and you can, like, type in 300 characters on your screen without going off the end of the line, and I can only type 80 or so and have y'all see it. No punctuation is used to end statements. We don't have to put that semicolon there or however your programming language dictates it. Your program statements begin with lowercase letters. Now that's awfully picky. I'm not going to count you off if you write some pseudocode and you'd use the word input with a capital I and you'd begin, right? I don't care if you use capital letters, but technically the book says make them all lowercase. Drawing a flowchart. I'm almost tired of lecturing through the PowerPoint and wanting us to do some more code, but the longer we delay it, the longer it's going to take to get to chapter 2 out of this introductory chapter. Okay, what is a flowchart? It's a series of symbols that represent logic, like that. If we look at it, this logic is real familiar. Except again, they're multiplying by 2 rather than dividing by 2. Start. Input my number. My answer equals to my number times 2. Output my answer. It's the same thing as this, except it's in graphic form. Now, if you're going to write a 3-line program, you can probably visualize it in your head and not have to write the pseudocode and not write the flowchart. I'm not going to make you write flowcharts for every program, but I will assign some flowcharts for y'all to draw. Things to notice about the flowchart. They begin with the word start and stop. This input and this output are in different shapes than that. And the shapes are important, and if you don't get the shapes right, then you get points counted off in your flowchart. Math is always done in rectangles. And input and output is always done, and I'm going to use a silly term, tilted rectangles. What's a better term for a trapezoid or quadrilateral? Well, unfortunately, trapezoids and quadrilaterals are also, rectangles. So I like calling them tilted rectangles. We all understand what a tilted rectangle is. So input and output statements are done in those. Math is always done in a regular rectangle, and then there are some other shapes as well. And if we mix them up, if that was done in a regular rectangle and that was done in a regular rectangle, you wouldn't get full credit. It's not that hard to learn them, though. So repeating instructions. The program only works for one number, right? If I wanted to divide by 2 on a different number, I have to actually run the program again. I might not want to run the program 10,000 times in order to, process 10,000 pieces of data. Well, what if I wanted to run it twice? Here's what I could do to make it run twice. Don't do this, but I could copy paste, right? Here's all of my code. I'm going to copy paste it a couple times. All right, now when I run it, like I said, don't do that because I'm going to undo it. Please enter number 100. Please enter number 200. Please enter number 300. Right? It's kind of cool, but not really. It's still got a limit, right? And now we've copied and pasted, meaning that if we make one change, like what if I felt like I needed to add a colon there, and then I'd have to remember to go and fix it everywhere as well as just at one place. When you start copying and pasting code, you need to think to yourself that that was a mistake. I need to find a way in logic to handle it. Copy and pasted code is just a bad thing, because if you make a logic error in it, then you've made logic error 3 or 4 or 5 or 100 different times. So you don't want it to work like that. We would want to put it in a loop so that it would keep running over and over, maybe until the user decided to stop it. I'm not going to show the code for putting it in a loop, but you already conceptually have the idea, right? Just keep repeating. Like the instructions on shampoo: wash, rinse, repeat. How many times are you supposed to do that anyways? It doesn't dictate. So, a programmer could use up the entire bottle, washing and rinsing and repeating, not knowing that they needed to stop. We're going to need to take a break soon, in my opinion. This is the example of the copying and pasting. You're just repeating the logic over and over and over. And if you wanted to do it 10,000 times, you copied and pasted it 9,999 times. That's ludicrous. Instead, you need some kind of loop. This is not a good loop because it never ends. The program runs forever. Sure, we can click the X button, right, in the corner. Back in old days, things didn't have close boxes, right? You just ran on a green screen terminal, If you got into an infinite loop, you might have to turn the computer off. And if it was a great big mainframe, then they'd be very angry at that. They had to reboot their great big giant computer just because your program had an infinite loop. Now, yeah, operating systems are supposed to have ways of closing programs or stuff upon request, but we don't want to write infinite loops. I'll give you an example of an infinite loop, just to show you, and it's going to show what a loop actually looks like. So you might want to type this if you feel like it. You don't have to. I'm going to write a loop that goes from 1 to 10. So I'm going to set x equal to 1. Then I'm going to say while x less than equal, the less than is the shift comma, 10, colon, parentheses x. And then I'm going to print a done message. Print parentheses quote done. All right, now my program has a logic error. not going to run correctly. It's not going to crash. It's just got a logic error. It's not going to do what I wanted it to do. It's just printing out 1 a bazillion times. Because I never change the value of 1. I never add 1 to it. So what I should do is I need another line of code that says x equals x plus 1. Now it's going to run correctly. And it does count. So that was a logic error. But that's an example of a loop. We saw a demonstration of an infinite loop. It didn't do me any good to see the number 1 printed out a million times if what I wanted was to see the numbers 1 through 10.
I got a question.
Yeah.
So, what about the previous program that we wrote, or line of code? Does the Python not just ignore that? Oh, wait, never mind. It's here.
Well, this stuff up here, it's not going to skip this stuff. Right? It's got to start from the top and keep going all the way to the bottom. So it's like, you know, you're rehearsing a song and you say take it from the top. It's got to go. It's got to do all of this, even, and that becomes annoying, right? When we're testing our program. So I try not to make it so that we have to enter too much data, because it would be annoying if every time we ran it we had to type in, you know, 10 different values in order to get to the good stuff down here at the bottom. But that's just a side effect of the fact that it's top down. It's got to go from the top to the bottom. So this is an infinite loop. If it's that kind of thing where it says input a number, you know, you type in 10 and then ask for input another number and 20, and it's an infinite loop. You might make it where you ask the user if you want to continue. Do you want to continue? Y/n. And if they type in n, then you stop. Or enter a number, or 0 to quit, right? Or Q to quit. That kind of thing. Give them a way to get out of it. That way to get out of it is called a Sentinel value. Testing a value. A decision symbol. Diamond shape. Here's how you check to see whether they were able to get out of it or not. Well, they keep giving you bad examples. And they don't give you a good example? Oh, for Pete's sake. All right, well, then we will see this bad example here. That diamond is a decision statement. Input a number. Is number equal to 0? If it is, then stop the program. That 0 is the Sentinel value. It's the number that stops the program. That's important enough that we're going to add it to our notes, and then I'm going to ask that we take a break. So let's go here and just put something like a Sentinel value is a value that stops the program. For example, please enter a number or -1 to quit. The -1 is the Sentinel value. And you've heard of a Sentinel, right? Or a sentry. A Sentinel is a symbol, you know. Sentry is something that stops the person from coming into the castle, or, you know, anyways. It stops the program from running when that value is entered. Or please enter a number or Q to quit, right? In that case, Q would be the Sentinel value. All right. Let's stop. Let's plan on being back at 127. Yeah. Anyways. Anybody get syntax errors out on the side? Go towards the back of the room. Oh, I never turned the lights back down. I guess it was visible. If anybody ever needs a change to it, if it's the screen's out of focus or the lights are too bright, this has been working for everybody. Been running without your It's not going to now. Now that we've added the last comment, you better put those last triple quotes, or else it's going to stop running. Okay, gang. Let's see what about 5 minutes. All right, gang, I left the recording going. Guess anybody watching it gets a great big amount of time that they have to fast forward. Oh well. Better to leave it running than to shut it off and not resume it.
Are we gonna make it through chapter 2?
Yeah, we're just about to hit chapter 2, I believe. Let's look at the PowerPoint. Do we actually want to draw flowcharts this time, or do we want to press boldly on? Kind of want to press boldly on. All right, 3 more minutes of lecture on chapter 1. Just because these might show up as quiz questions, and you know that you can retake the quizzes as often as you like. So understanding the programming environment. What is a text editor? It's just something you can type text into, like this. You wouldn't want to write a program in Microsoft Word because it doesn't create text, and it instead creates some special format, you know, that can embed fonts and pictures and stuff like that. And yeah, you can then try to do a save as text, but you wouldn't want to. Instead, you want to use a text editor. Every copy of Windows comes with Notepad, so in a pinch, you could write some programming code in Notepad, but it's not really the best thing to do. Instead, you'd want to use a text editor that's built into your programming environment of choice. We have one built into idle, right? Every time we do file, new file, we get a text editor. And that's what we need. There are other development environments that are considerably more complex than idle, but they still have a text editor embedded in them. I could launch Microsoft Visual Studio, and you'd see that it has, you know, a million little different menus and drop-down boxes and, you know, palettes on the screen and stuff like that. But fundamentally, it's still got a text editor so that we could enter our program, and it's got some other buttons for debugging and running your code. So you need the text editor, and then the bundling of an editor with the code necessary to compile and run it is called an IDE, Integrated Development Environment, which we can kind of see where the guy got the name for idle. That adds a compiler, an editor, and other programming tools. For example, I mentioned Microsoft Visual Studio, or idle. Right? We're using idle. The command line is where you type text entries to communicate with the computer's operating system. Now, we don't have to use the command line because idle gives us a shell in which to run. When I run the program, it gives us a shell. If it did not, I might have to launch what's known in Linux or Mac as the terminal, or what's known as in Windows as the command line, the command processor. I would like click the search button and type in CMD, and we get the command prompt, and we could run our program that way. Yeah, let's see if I can actually run my program from the command prompt. I'm going to CD into my code directory, 1113. I'm going to find one. I don't know if you can see these little things I'm typing. Black, white. Yeah, let's make the font bigger. That's a little bit better. Okay, so I did some CD commands to get into the right directory. And I'm doing a dir command in order to find my program files. And I'm going to try to run Python. I'm going to try to run lecture.c.py. So I'm going to type Python space. You don't have to do this. It's just background information. Python space lecture.c.py. Now this looks familiar. Please enter a number. 100. The result is 50. 1, 2, 3, 4. Right? It ran our program. That's running a program from a command line. Almost any Windows program can be launched from the command line, actually. If I want to start Notepad, I can just type Notepad. Right? If I want to run Word, I might be able to launch it. Let's see if I remember the command. WinWord? Nope. Word? Nope. Oh well. It's all right. If I knew the exact path to it, if I knew which directory to CD into, I could then launch Word on the command prompt. It's just not what is in the search path. Now we're kind of going off the track, but if I type path into the command prompt, it tells me the search path. If a program is in any of these directories, it'll run automatically. Now, however, Word and Excel and stuff is not in the search path, so I can't run Excel from the command prompt. I could add it to the search path if I wanted to. Through the operating system, I'd have to find a way to do that. However, we notice that C:\Python 37 is in the command path, is in the search path. So that's why I'm able to run the Python command. And it just takes me into the shell. Just like idle launches into the shell when I first run it. If I close all my windows, and then I launch idle again, we see it takes me into the shell. What is the shell? It's just the interactive Python, right, where I can type commands in, like print 10. And it prints out 10. Well, since I ran the Python shell here, if I say print 10, it does the same thing. We're not going to do very much with the command prompt because we can do it all with idle because it's integrated, right? The shell and the text editor are integrated together. So the command line is when you're just typing commands in, right? A graphical user interface, or GUI, is when you have windows and buttons and stuff, right? Back in old days, you didn't have windows and you didn't have buttons and drop-down dialogues and stuff that, right? Like in the 60s, you know, you sit down, you just typed at a computer and you didn't have a mouse. You know. Oh, by the way, you know that before mice, there were trackballs. This is just for grins here, you know, but you know what a trackball is. Trackball is just something with a little ball to move around like a mouse. That was actually a pretty cool invention. First trackball. Check that out. That's a bowling ball. Moving your bowling ball in order to move the cursor around, right? Very quickly, of course, they started making smaller balls because that's absurd. But yeah, in the 50s or whenever that was created, and if you had to move a cursor around on a screen, maybe you're moving a bowling ball. I'm sure that's just like a, you know, a prototype at MIT or something. Here's a later one, right? Anyways, I always find the history of programming interesting. Now, what about mice? Nowadays, we use laser mice, right? Before that, there were mouse balls. And you probably remember, you know, having to pop the ball out and clean it with alcohol because it got gunked up or whatever. Before that, mice were really kind of annoying because they just had two wheels. They had a horizontal wheel and a vertical wheel. So if you wanted to move your mouse forward, you had to tilt it a certain way and roll it up. And if you wanted to move the mouse horizontal, you had to tilt it another way and move it to the, you know, left or right. And if the wheels got smaller, maybe it would support diagonal movement, but at first it didn't. That would have been the 60s right there. Late 60s when the mouse was invented. Almost. 3 pages left, it looks like. No, there's more than 3 pages. But we know what a graphical user interface looks like. Here is what our program might look like if we'd written it as a GUI, as we'd written it as a window. Please enter a number, 13, and as soon as they hit the enter key or click some button that's not there, 13 doubled is 26. Now it's cool to be able to do it like this. Hopefully, towards the end of the semester, we'll have time to write some programs that look like this. However, it's considerably more difficult, considerably more complex to handle drawing a window on the screen than it is just letting the user type in something into a command prompt. So the evolution of programming models. People have been writing modern computer programs since the 1940s. The Americans invented computers in order to build better weapons during World War II. You know, bomb sight calibrators and artillery, you know, tabulators and tables of, you know, angles to fire things at, and, you know, really the way the war with Japan was ended is to do all the calculations to create atomic weapons, whereas the English, the British, used computers in order to crack the German codes, right? The Nazi Enigma machine was the code maker that they used. that the Germans used, and so when those messages were intercepted, they needed to be decrypted, and it was an incredibly tough challenge, and so, you know, the British math whizzes, you know, made computers to do that, so it's kind of a parallel evolution. So newer programming languages are not all zeros and ones, they look more like natural language, right? Maybe I showed you what assembly code looks like, maybe not. Well, this is really blurry. But maybe if I click it, it'll come into focus, I hope. Maybe not. Yeah, there we go. Okay. So there's just those pure numbers like I wrote at the very beginning. Here's the assembly language equivalent. It's just got a couple of little keywords, but those keywords get turned into these numbers, right? These opcodes. Well, we wouldn't want to have to write software like that. Nowadays, almost nobody does. Nowadays, almost nobody is an assembly language programmer. Instead, you write in a higher level language. This is what's known as a low level language because it just gets transferred directly into the opcodes, the machine language that runs the processor. The problem with assembly is that it's very platform specific. If I wrote something to work on my Intel processor, then that same series would not work on my ARM processor that I use on my phone, or, you know, on a different operating system, you know, Macintosh rather than, you know, than Windows or something like that. And so assembly language is not cross-platform compatible, whereas something like Python is. You write a Python program, it'll run on, you know, you can download Python for your tablet if you want, or you could run it, you know, on your little Arduino box, you know, if you're interested in experimenting, you know, with little tiny, you know, computers that can drive robots and things like that. So we use a high-level language that looks more like natural English and supports algebraic notation. What is algebraic notation? The ability to write something like that, right? We would not want to write move move address this into register whatever, move address this into whatever, if we could type that. So newer programming languages, easy to use because they look more like natural language, and we can create modules that can be strung together in a variety of ways. We don't just want to write one long monolithic piece of code that's 100,000 lines long. Instead, it needs to be broken up into modules, just like all the information, you know, in a university library isn't written into one big million-page book. It's divided up in a whole bunch of books with a whole bunch of chapters. That's the equivalent of modules. The good thing about modules is that they can be reused. I write some really cool math libraries, some really cool math modules. I can plug them into another program without having to rewrite them. You know, just like books can be loaned between libraries, or you can go and buy a book, right? Same idea. Nowadays, broadly speaking, there are two major models or paradigms used by programmers. And I know that this is getting a little bit abstract and it's a little bit boring, but we'll go back to code in a minute. There's procedural programming, and then there's object-oriented programming. Procedural programming is what we've done and what we will continue to do. It just means telling the computer line by line what we're going to do, what it's supposed to do. Like this. Here's a procedural program. Hey, please enter a number. Then input X, turn it into a float, do some math, output something else, right? Line by line, we're telling the computer to do something, and we're treating, you know, kind of top-down programming. Object-oriented programming is when you cluster data into objects. What does that mean? It might, don't type this because I'm making this up totally off the top of my head. Right. Create data. Data.x.input. Data.x.calculate. Data.x.show. Something like that. It looks very, very different. And the logic for what the input and the logic for the showing of the output and the logic for doing the math is hidden away inside an object, right? Our program, the code that we're writing, doesn't know how to do all that. And we created a turtle program, right, where we drew shapes on the screen? Yeah. So We created a turtle program. That was object-oriented programming. We didn't have to write the code line by line that told it to draw a circle. That would take hundreds of lines of code for, some dummy like me who doesn't know how to draw graphics. It'd take a lot of research. Instead, I'm just able to bring these modules in, create a turtle, which is an object, and start feeding it commands, right? Go left, go right, change your color, that kind of thing. So that's object-oriented programming. It's a different concept. We're going to be doing procedural programming, where we start at the top and we get pieces of data and we move them, and we don't bundle them all together into objects. What is an object? It's a collection of data, and then the functions, the commands that use that data. What kind of data does a turtle need? It needs an X and a Y position on the screen. It needs an angle that it's going. It needs a color and a speed. It needs a pin thickness, right? That's a lot of data to contain just inside one variable, T or Leo or whatever we call it, our turtle, right? And then it had some functions that it could execute, a forward and a left and a right and a back and a circle command that used that data that it was storing. Let this be the last one. All right, here's our summary. We know what hardware is. It's the stuff that you touch. We know what software is. It's the stuff that makes the hardware do something. Accomplishes input, processing, and output. Your logic has to be correct. Logic errors are much more difficult to locate than syntax errors. Syntax errors show right up. The program doesn't even run, although they can be subtle. I may have demonstrated this last time. I may not have. But it doesn't always show you the right line for the syntax error. Let me give you an example. That's just Notepad. I need to close that. Although it was a good example. Right. Here's an example of a syntax error that shows on the wrong line. Look where it's showing the problem. What is the problem? You probably saw me make the change. I took the closed parentheses off the line above, but it's flagging the problem as being on the next line. And if I had a bunch of comments or something, like, now that we have the data, perform the calculation, right? There's a lot of distance between there and there. So when I run it, boom, it's showing me the syntax error, and I can pull my hair out trying to figure out what's wrong with that line of code. If that's the case, if you're pulling your hair out looking at a line of code, it doesn't look like a syntax error, scroll back to the next non-comment and see if it's on the line above. Look for missing parentheses, look for missing quotes, stuff like that. What if yeah, that's a big enough example of that. So syntax errors are fairly easy to find. Sometimes they're a little bit harder to find like that, but logic errors are much harder, right? You can have 10,000 lines of code and one logic error in it, and you'd have to figure out why it's giving, Examples of logic errors. The Patriot missiles that were used to shoot down, the Iraqi Scuds during, the Gulf Wars. The anti-missile systems had a timing error to where you boot it up, and then slowly over time, the longer the program is running, the more the time drift happens, so that the missile would be fired, a second and hit, a target where the incoming missile was not. And that timing error got worse over time. If the computer was left unbooted for 2 days or 3 days or 4 days or 5 days, you didn't notice it, right? Because you turned the thing on, you test fired it, it worked perfectly. But if you left it running for a week, then it no longer worked perfectly and it started missing, that's a logic error. There was a problem. Well, they learned how to fix it, right? You just turn it off and turn it back on at the beginning of each day, and that fixed it. But it didn't really fix it. Somebody had to find, the timing error and fix it. Another logic, no, don't give too many examples. One more. Very expensive one. You know how you send you know, space probes to land on Mars or whatever? That's actually a very, very difficult problem. A lot of Russian space probes to Mars crash. A lot of American space probes to Mars has crashed. Not so much recently. Recently they all seem to work because they are tested extraordinarily well. But one in the 80s got to Mars, then turned directly towards it, fired its engines, and slammed into it. Brilliant. The reason why is because the modules were written with the expectation that the data being fed to it were in English units, you know, feet and miles and stuff like that, because the earlier modules, the earlier landers had been written so that their sensors returned values in English units. But, you know, modern world, we're going to support metric. Whoever wrote those modules wrote to the specs that, you know, they were going to use metric units. And so they disagreed, you know, if we had bad data, it slammed, you know, something that cost $800 million to build, you know, into the planet. Logic error. So you use flowcharts and pseudocode to try to eliminate logic by knowing what you're doing before you actually start writing your program. Infinite loops, you don't want them. So you can ask for a Sentinel value, the value that'll stop. Now you have to pick the Sentinel value yourself. You have to decide what to tell the user. You know, they're supposed to type, whether it's a Q or a -1 or whatever. And you use a text editor or an IDE to enter your program statements. All right, we are done with chapter 1. Let's veer off and talk about our book for a minute. We ought to be able to get our book going, up and running. If we go into Cengage and click the links, pretty much any of them, let me switch to student mode. We go into modules. There's a whole bunch of stuff up here you can read, but basically you want to be able to get to chapter 1. So you want to be able to click read chapter 1. But the first thing I would do is I would click, let's just click on read chapter 1. It says this tool needs to be loaded in a new browser window. All right. Hopefully I don't have any pop-up blockers installed. I click that. It goes to this page. Welcome to Cengage. I already have an account. I'm going to pretend I bought Cengage Unlimited or whatever. I should just be able to type my account in and my password, and it hooks everything up. If you do not have an account, I believe that there's a way to purchase the book at this point. Purchase access to it. Just whip out your credit card and you can buy it. You don't even have to go to the bookstore. On the other hand, if you buy it from the bookstore, maybe you can turn a receipt in and somebody will give you money back for it. Who knows how that works for you? Want to make sure everybody can get to this screen, and I'd like for at least a few people who got Cengage Unlimited or whatever to actually show me that you're able to get to the book, so I can prove it to everybody else. Yeah.
How do I get rid of this? Or just get rid of this whole thing?
Oh, good question.
Go to the right side, and then there's a book. You go in.
This one, the full book?
Yeah.
Ah, sweet. Thank you.
All right, I want to know how to do that too, so show me.
Just that I just go to full book.
Oh, full book? Okay. What does that mean? Overlapping enrollment records. I swear, guys, I've been using it for 2 years and I haven't gotten this message. What I'm trying to get us to is that everybody who's logged in, I want to start the Chapter 1 test, just to show you how to work your way through it. And if you haven't started it, that's okay. We're not going to work our entire way through it, but I'm trying to go with this.
So we can keep trying.
Right. If it doesn't work this time, I'm going to give up. I don't want to prejudice y'all, but I will say that I do not particularly like this thing here.
You want to start the assignment now?
All right. Never seen the like. But first you don't succeed, you launch a different browser. I think I told y'all that. You can't get into Cengage with one browser, try it with another. Come on, Firefox. Come on, Firefox. Don't make me sorry I chose you. For Pete's sake. Alright, forget it. I get to talk to Cengage tech support. It's exciting. But you're able to get into it. Who else? You got it? Got it. Just gonna be wandering around. Anybody having trouble getting it?
You want us to start now?
Don't bother. I mean, I can't work my way through it with you. Let's see. Go ahead and start it, and let's see if everybody gets the same questions at the same time. So go to the Unit 1 test. They call them tests, not quizzes.
Bunch of it. Chapter 1 quiz and Unit 1 test. Yeah. But let's go.
I got you.
You want to take the one that says test, not the one that says quiz. Okay, so what's the first question?
Writing a program in a language such as C++ or Java.
So writing a program in a language such as C++, Java is known as underscore. Is that what y'all's first question is, or are they randomly ordered? Okay. So what is it? Writing a language, writing a program is known as
Coding.
coding. Yeah. So you can just choose coding.
Oh.
That's the next question. Here it is. Which of the following is an example of a syntax error?
All of the above.
Producing output before accepting input? No, that's a logic error. Subtracting when you need to add? That's a logic error.
Misspelling.
Misspelling, a typo, grammar mistake. When you write a program that will run in a GUI environment, you do not need to plan. That sounds silly. Its logic is very different. That's likely. Users are more confused. Hopefully not. And some syntax is different.
syntax is different.
Let's go with some syntax is different. I hope that they don't want the logic is. To me, it looks like there's two different choices there. But we're going to go with some syntax is different. Yay! All right. A programming language's rules are its, not its logic. The rules that it has to follow when you type it in.
Formal.
Syntax. Syntax errors.
Good.
I know logic is seductive. It's the choice that you might grab. The major computer operations include hardware and software, input, well, an operation isn't hardware. It's looking like input, processing, and output because sequence and looping, well, yeah, that's kind of important, but I'm going with input, processing, output. And I hope I is going through this too quickly. I'm not figuring out. You can always review it by going through it again.
So just like the exam one.
When you use an IDE, the logic is simpler? No. The logic is more complicated? No. Some help is provided? Yeah, it's trying to help you. It may be popping up options to fix your grammar. When you do when you try to run it, it'll show you the syntax error. That's the purpose of using an IDE to make programming easier. Oh. Got it. The term EOF, well, we didn't even see that in the PowerPoint, I don't think. Take a guess what EOF means. Yeah, end of file. I don't even have to see the options on the screen to guess that. So you're going to want to choose a logic flow? No. A standard input device? No. A generic Sentinel value or a condition in which no more memory is available? Okay, it's going to be a generic Sentinel value. Let's write that as complex as possible. But we said that the Sentinel value indicates the end of input. So end of input, end of file. Let's go with that generic Sentinel value. I'm sure the text says that in the PowerPoint did. Which of the following is temporary internal storage? A keyboard is not temporary internal storage. A hard disk is not temporary. That'd be bad news, right? Every time you turn your computer off and the hard drive is erased, hopefully not. Random access memory is internal temporary storage. So in other terms, memory. CPU uses memory, but it's the thing that's actually doing the math and stuff like that. The parallel in a flow parallelogram. They're not calling it a tilted rectangle, they're calling it a parallelogram. There's a couple of shapes we've seen in that flow chart. I could just go back in the PowerPoint, point them out, in which case I don't need to do that. All right, rectangles are known as process blocks. Parallelograms are known as data blocks. Parallelograms, tilted rectangles do input and output. Is there a choice on the quiz that looks like that? Either A or B, okay. The decision symbol. It's not a lozenge. I like that shape. That's the word that I use for oval. That's the decision, the diamond. And you're really going to have to learn those, so don't just let the fact that I'm giving you all the answers right here. Well, I didn't give you the answers. You did that one. Excellent. But don't get the fact that you're going through it quickly hinder you from learning that. I would recommend taking the exam again. I'm just making sure that we all know how to do it. As compared to procedural programming. With object-oriented programming, the focus differs. You cannot use some languages such as Java. You do not accept input. Okay, I'm going to rule out the error that says, accepting input, that's definitely not the wrong answer. You do not code calculations? No, that's absolutely wrong. You cannot use some languages such as Java? Okay, well, Java is an object-oriented language. How are you supposed to know that? Maybe the book told you. There might be some languages which are still non-object-oriented, but not hardly anymore. So I would choose the fourth answer, the topmost one, I guess. The programmer's focus differs. That's a weird way to say it, in my opinion. But the way you write the program differs, so I guess you call it the focus differs. Instead, you think about blocks of data. I have a printer, and it has several commands. It has a print command. It has a, remove item from queue command, stuff like that. What's the next question?
Computer programs are also known as blank.
Yeah, computer programs are also known as not data, not hardware, not information. Computer programs are known as software. Which of the following steps is in the correct order? Yeah, you don't code it and then translate it in machine language. We don't need to do the translation. You test the program and translate it in. Okay,
That was the first one.
that's not right. Okay, the first one may be right. Put the program into production, understand it. No, you don't do that first. Code the program, plan the logic. No, you plan the logic first. The first answer is actually starting to look really good. You write the program, and then the compiler turns it into machine language. Yeah, so that's a good answer. None of them look real good to me because to me you don't translate it in machine language, but the compiler does. So. An English-like programming language is not binary level. Binaries are zeros and ones. It's not a low-level language. It's a high-level language. If it looks like English, if it's got words like print or input, stuff like that, then it's a high-level language. The two most commonly used tools. This is silly. Word processors and spreadsheets? No. Flowcharts and pseudocode? Well, the textbook mentioned it. Let's keep going. Java and Visual Basic? Well, there's a million programming languages. I wouldn't just pick those two. ASCII and Epsidig? What in the heck are those? We have no idea what those are. Yeah, you do. I'm leaning towards saying that flowcharts and pseudocode are the tools for planning logic. Epsidig and ASCII are ways of storing data on disk. Epsidig is obviously. How many more questions we got? 16 out of 20. The most important task before planning the logic. You don't code it before you plan the logic. Maybe understand the problem. That's looking tempting. Train the users. No, you don't train the users before the code's written. Decide which programming language to use. Well, that's interesting information, but once you have the logic, you can code it in any language. So understanding the problem would be the best answer. In a flowchart, what is a rectangle? Well, it's not input. It's not a question. It's not a Sentinel, just because Sentinel is something that they type in. We don't see that on the flowchart. It's a, what do they call it, process? Yeah, it's a process block. Yeah, the rectangle is the process block. I called it math, but the special term for it is a process block. The most important task of the compiler. The compiler does not execute the machine language programs. That's the computer's job. Translate English statements into a language such as Java? What? No, that's taking my job away from me. I'm the one who needs to translate the pseudocode into Java or into C++ or Python. Translate a programming language into machine language? That's looking real tempting. Create the rules? No. What does a compiler do? It translates the high-level language into machine language. Visual Basic, C++, and Java are what?
Programming.
Yeah, they're programming languages. So is Python. Which of the following is a logic error? Boy, syntax error is a misspelling or grammar error. So performing arithmetic with a value before inputting it? Yeah, that would be a logic error. Dividing by 3 when you meant to divide by 30? Yeah, that's your fault. You coded the program wrong. Accepting 2 input values when the computer requires only 1? Yeah, that's illogical. I'm kind of liking all of the above. That's the last one? Woo. Bet you made a good grade.
95.
Well, let's review this test and find out what we missed. Or does it show us? Yeah. All right. Hopefully you got an idea of you can take it again. Oh, I'm so angry at Cengage. What does that even mean, duplicate? Wasn't like that when I... All right. So be it.
Maybe your emails go to two different accounts. That's where the confusion is.
Well, I could try raider.rose.edu, but I've never logged onto it with that account. Oh well. Good thing we have a tech support link here. And again, I forgot to pause the recording, so for everybody who's listening, I hope you enjoyed not having anything on the screen. Well, this is going to be fun. To get technical support, you have to log in. Whoa.
There you go.
All right, I'll work on this later. All right, we're done with chapter 1. Let's take a peek at chapter 2. And we're going to think about some homework assignment. If we're going to do some homework, we better have some more examples of code with which to play. We already have one example, but I'm going to want to change it. We're going to write something that looks very similar to that one that was dividing, but instead we're going to do some multiplication, just like the book showed. So here's the problem. I'm going to remove those triple quotes and just keep going with my comments. Yeah, this is our programming task. Write a program that will ask the user for the value of x and will print out x times 2. This is going to be almost the exact duplicate of the code that we wrote up above, but there's going to be one minor change. Print parentheses quote, please enter the value of x, end quote, in parentheses. X equals input, parentheses, in parentheses, but I like having that little greater than sign telling them where to type. So I'm going to go ahead and do quote, greater than, end quote, just to let them know where to type. We need to turn it into math data rather than string data. String data is keyboard data. You can't do multiplication on keyboard data. We have to do it on numeric data. So x equals float parentheses x. And I'm going to add a comma here. What in the world does that do? Convert keyboard input into a number. And what does float mean? It means it's a number that supports decimal points. There's another data type called int. But if we put an int there, it's for whole numbers only. And if the user types in 1.25, it'll crash. So we're going to make it float. Now we're going to do the multiplication. Result, or I could call it R or Y. You know, variable names only matter to us, not to the computer. Result is equal to x times 2. Now I'm going to say print parentheses result of x times 2 is, end quote, comma, result. Alrighty. That would solve that problem. But I haven't tested it. I better run it. Yes, ma'am. Let me test it on my side, and then I'll come back there to you. Please enter the value of x. All right. 1 million. All right. X times 2 is 2 million. All right. I'm happy with it. Yes, ma'am.
Okay, if it's all green, then that's interesting. Because we have our single quotes versus double quotes. If you use single quotes here, you better use double quotes down here, and vice versa. So let's use double quotes there. Let's get rid of set all this. So yeah, it's easy to do that.
In this language, single quotes and double quotes are interchangeable. In a lot of other languages, it's not. But if I type this, single quote, single quote, single quote, and I type in a bunch of stuff, it looks great because it's green. And I use double quote, double quote, double quote to stop my explanation. And then I say A is equal to B. It's still green. They have to match. So you just pick one. If I use single quote, single quote here, then it starts working. But I've been using double quotes everywhere else, so I'm just going to settle upon that as my standard. So it worked for everybody. All right. Let's make up a homework assignment based on what we've got here. Assuming you have Python installed at home. If you haven't yet, it's a little bit of a problem. You're getting behind on homework maybe, but you can also use an online version of Python. right? Online Python 3. I'm just going to copy the address of one of these. So why don't you do all your homework with that? Because if we start using turtles and fancy stuff like that, the online versions of Python might not support it. So assuming you have Python and idle installed, if you don't, use that website. You don't have to type that right now. I always upload the homework assignments. But here's the meat of the problem. Write a program that performs the following tasks. Ask the user for value n. Just call it n this time rather than x, just for variety's sake. Display the results of the following calculations. In *2, in *2, in divided by 2, and in //2. So what's the difference between all this? ** means to the power of. Most languages don't have a to the power of operator. Instead, you have to call a function, but Python does. What do I mean by that? Let me launch a Python shell. And I'm going to say print 10 to the power of 2, *2. And to the power of 2 means times itself, so that's going to be 100. That's what ** means. Well, we know what the slash means. What's about the double slash? That means floor division. It's a fancy word for rounding down. So print 3 divided by 2 is 1.5. But print 3 //2 means do the division and round down, which is just 1. And again, a lot of computer languages don't have that option. Python does. Okay. And then as part of the assignment, I'm going to explain what ** does. By the way, ** means to the power of. And // means floor division, which means divide and round down. Not round to the nearest. If it's 1.9, it's not going to go to 2. It's still going to be, 1. 1.99 floor division rounds down to 1. All right, that's our assignment. I don't mind ending at this point, 10 minutes early. Rather than start chapter 2. So this is just like our program, except we've got more to do, right? It's not just multiplying by 2 or dividing by 2. It's doing 4 different things. How are you going to do that? Well, you might make it result 1, result 2, result 3, result 4, or you might just calculate a result and print, calculate a result and print, calculate a result and print, calculate a result and print. And if you get stuck on that idea, just go ahead and text me and I'll help you. Are there any questions over it? Is that kind of making sense? If you use the online version of Python to do your homework, you better take a picture of it because once you close the window, it's gone, right? And I would appreciate it, make it mandatory as a matter of fact, that you copy that and you save it, right, as a notepad file or a Word file or something and submit that to me as well. But for this early assignment, I don't care if you just send me a picture of it, right? But if you're doing it at home, I want you to go ahead and give me the source code. I mean, if you're doing it with, with idle. All right, let's pretend that we're going to, that this is homework and we need both the screenshot and the source code. I don't make y'all do screenshots for the lectures usually, but just to pretend, make sure we're all on the same page. We need a Dropbox. All right, now last time I did this, it didn't let me pick what kind of data they submitted. All right, here we go. All right, now we're good to go. We should have a lecture C. C finished chapter 1, but it's not showing up. We'll publish it. All right, refresh your assignments page. It'll be there now. I'll prove it to myself by going to student mode. And for those of y'all who have already used Canvas, I'm sorry, I know this is repeat information. I'm just making absolutely sure so we don't have any more questions. Student view, assignments. Lecture C. Now, before I actually start trying to submit, I'm going to make the screenshot so that I have two things to save at the same time. So, assuming that I've run the program, I go to idle, I run the module, whatever. It doesn't matter for this time. I'm going to hit the print screen button. I think we all know where it is now, upper right corner, near the numlock key and stuff. Now I'm going to open up Word or Paint so I can paste. I'm just going to use Paint. I'm going to paste or hit Control V like vehicle for pasting. And I'm going to save as. And I'm going to put it into my homework directory, my code directory. So it's going to go in the same directory as my source code. And I'm just going to call it lecturec.png. Or if you chose a JPEG or whatever, have a different extension, but make it a PNG. Doesn't matter what format you pick, but make it a PNG. All right, now I have two files to upload. So I can click Submit Assignment. I know I'm going a little bit faster than y'all, but y'all are smart. Choose a file. Go to my program directory. I don't like the data being sorted with pictures, so I'm going to click on this little thing here that says More Options, and I'm going to support it by details. Or I might be able to right-click and do View Details. Then it's real easy. I see my file extensions and everything. I want the PNG, the screenshot, and add another file. Choose File. I want lecturec.py, my program file. And I can add a comment if I want. This was an amazing lecture. And now we're done. Now it's uploaded. Why did it say no comment? I put a good comment in there. Oh, no content. Okay. All right.